Okay, today we're going to finish off multiple linear regression, and there is one more thing that we didn't discuss yet, is how to include in multiple linear regression predictors which are not continuous. I don't know if you realize that or not, but in multiple linear regression, everything that we did so far was predicting continuous target, which is by definition what multiple regression does, right? It predicts the continuous target variable. But the predictors that we were using were all continuous, always, right? So in the recent, for example, exam, remember you were predicting what? University GPA, right? Based on three continuous variables, right? SAT score, high school GPA, and number of hours of activities in high school, right? All of them were continuous. When we discussed Toyota Corolla, in fact, go ahead and download Toyota Corolla, okay? We're going to use it one more last time, okay? So, Toyota Corolla file, go ahead and download that, and double click, open up. In Toyota Corolla example, we predicted the price of the vehicle, right? Based on the age, mileage, and something else, I can't quite remember, what was that? Horsepower? Yeah, horsepower, right? We use these three predictors. But if you look at the list of the variables, it also includes fuel type, right? Cars can use different fuel type. And look at that. The possibilities are diesel. Well, it says petrol. What does petrol mean? Petrol is kind of European way to say gas, right? What Americans call gas, which is a little weird. Gas, natural gas is also gas, right? And the car fuel is also gas. Okay, so cars can be diesel cars or gas cars, or if you scroll it all the way down, every once in a while you will see something weird that says this one, CNG. What's NG? Natural gas, right? So some countries drive their cars in a liquefied natural gas. Like for example, Turkey. Okay, in Turkey, well, I know that because I talked to one Turkish professor who was here at CNU, and he said basically that all the cars, so the country essentially switched, half of the country drives on the gasoline, and half of the car drives on liquefied natural gas. So the cars were retrofitted with tanks, so you can, you know, if you pull to the gas station, you can put regular gas, or you can choose liquefied natural gas. And either one can be used to drive the vehicle, okay? Another example of the non-continuous variable, categorical, is apparently that's a car color, right, metallic. And the answers are either 1 or 0. So 0 means, 1 means it's a metallic color, right? And 0 means something else, right? It can be white, black, green, orange, yellow, whatever it is, right? And then there is automatic. Well, automatic is self-explanatory, right? 0 means probably not manual shift, right? And 1 means automatic car, okay? So we never use them. Let's actually go ahead and see if we can get to use these variables in the model, okay? But before we do that, what I want, let's first build the model, and then I'm going to discuss how exactly Jump uses the categorical variables, right? Such as fuel type, metallic car, and automatic transmission. So let's go ahead. Same procedure. Fit the model, right? We're still doing the multiple linear regression, but this time around we're going to include more than just continuous predictors. So my target is price, right? That's what I'm predicting. How much is the car? And every other variable I'm using as predictors or model effects. So I'm going to add them all, and then click the run button, so there are no changes, okay? It's the same procedure. Okay, so here is my regression output. And let's go ahead and scroll down to the very almost bottom, right? We need parameter estimates, okay? So here is my summary that essentially gives me the equation of the regression, right? So there you go. Here's my intercept. So my equation essentially, and I can show the equation, right? I told you that before. Hold on, let's see if I can go ahead and do that. Regression analysis, regression reports. There should be an option that says show me the equation, right? Row diagnostics. No, it doesn't do that. Okay, or at least I can. Where is it? Show prediction equation, yeah. Where is it?
Under estimates.
Under estimates, okay. Estimates. Oh, okay, yeah. Show prediction expression right there. Okay, cool. So here is my model, right? That includes everything, every variable that I selected. So here is my slope. Oh, no. That's the intercept, right? Right there. And then age is multiplied by minus 132. So how do I interpret that? Just like always, right? If I keep all the variables the same, I don't drive the car, there is no mileage, the only thing that changes is the age, right? Car gets older by 1 year, so I don't drive the car for 1 year. What happens is the value declines by that much, right? That's our standard way to interpret things. So every year that the car gets older, it loses $132, okay? Then every mile that I put on the car takes out that much of the value, right? But look at that. Here is my part that kind of looks unusual, right? Depending on what type of fuel the car is using, I have to either add or subtract something to the equation, okay? And here's what happens, ladies and gentlemen. If you look at the parameter estimates, now, if you remember, we just discussed that. Type of the fuel used by the car, there are 3 values, right, in the equation. Car can be diesel, or it can be petrol, gasoline, right, driven car, or it can be liquefied natural gas, right? You can see that in my parameter estimates, there are 2 variables that were not part of my original set, right? It says fuel type CNG and fuel type diesel, okay? So here is the rule of thumb, ladies and gentlemen. Let me write it out, okay? Rule of thumb. Hold on, I'm going to create a new page. Yeah, right there. Rule of thumb is, if I have a categorical variable with, let's call it K categories, okay? K categories. Okay? Then I'm going to need K minus 1 dummy variables, okay, to represent that, okay? So that requires from me K minus 1, let's call it indicator variables. Okay? So for example, that's I'm going to show you a different probably example. Let's say I'm predicting whether or not a person, client of the bank, will accept a loan offer, okay, or will default on the loan, okay? And I want to use things such as education level, right? It may make sense that different people have different education level. So for example, let's say I have a variable education in my data set, right? My predictor. And it can be, oh, that's an ugly bracket, okay. It can be high school, that means they have high school and that's it, nothing else, right? Then they have a bachelor degree, or they have master's degree, or they have a doctorate degree. So these are my values, okay? So therefore, this is a categorical variable with K equals how many? 4 levels, right? 4 levels. So in order to represent these 4 levels, what I can use is 3 dummy variables or indicator variables. That's one of the practices, okay? So for example, I can say indicator variable I high school, okay, is 0 or 1. 1 if they have high school degree and that's it, okay? Or 0 otherwise, okay? So if they have bachelor, master, or PhD, that's a 0, okay? Then I have another one, variable that represents bachelor degree, okay? Same thing, 0, 1. 0 if they completed bachelor degree requirements, but nothing else after that, okay, above that, and 0 otherwise. 0 means it's either high school or masters or PhDs, right? And then another variable that I will have is B for the I for the masters, okay? 0, 1. So 1 if they have master's degree and 0 otherwise, okay? And that's it. k minus 1 is all I need to represent all 4 possibilities. How so? For example, if, for example, let's say there is a high school, let me write them out, okay? I high school, I for bachelor degree, and I for, whoopsie, what did I do? I for masters, right? Equals, equals, equals. So if a person, a client of the bank, has a high school degree, what are the values of my variables? High school, this one is equal to 1, right? And others are, the other two are zeros, right? 0, 0. So this combination 1, 0, 0 represents somebody with high school diploma and nothing else, right? What if I have a person with bachelor's degree? What are the values going to be? No, not quite. Bachelor is 1, high school is 0, right? I mean, it's implied that they have high school diploma. Yeah. What I mean is highest level of education. Right? What's your highest level of education? Right? High school is implied, right? All of these imply high school, right? If you have master's or bachelor or doctorate, you have high school, right? So that's implied. So the highest attained degree is bachelor. So that means that high school, IHS is 0, right? M is 0, but bachelor is 1. What if I have a master's degree person? Bachelor is 0, master is 1, right? What if I have a PhD? How do I encode that? All of them have to be zeros, right? So high school is, no, it's actually other way around. Hold on. All of them have to be 1s, right? So sort of, right? So if I want to encode, all zeros mean that none of them apply, right? They didn't even graduate from high school, okay? But if I have all 1s, that in my model will represent that they finished high school, they finished bachelor, they finished master, and they finished another one. I can encode variables in this way, okay? So to represent k categories, I need k minus 1 variables, okay? That's just general rule of thumb. If you have k categories, you need k minus 1 variables, right? So let's go back to our output, okay? In the output, in my input variables, the one that I had, the 3 actually variables that I had that were categorical were metallic color, yes or no, automatic transmission, yes or no, plus the type of the diesel, type of the fuel, right? It can be diesel, gasoline, or liquefied natural gas. So liquefied natural gas has how many different levels? No, not the type of the fuel, sorry. Type of the fuel. How many levels? 3, right? 3 different types of fuels. Natural gas, diesel, and gasoline, right? How many dummy variables do I see in the output? Fuel type 2, right? Same idea, basically. You have k variables, you need k minus 1 indicator or dummy variables to represent that, okay? But here is the deal, ladies and gentlemen. Unfortunately, and I don't know why they did it like that, by default, JUMP does it a little bit differently. So instead of 0, 1 encoding, that type of encoding, actually, JUMP does the dummy variables. So every time when you have a dummy variable, it does them as +1 and -1. Okay? So specifically, here's what it means for us. Look at that. We have 2 variables, right? 2 dummy variables. Fuel type natural gas -1063. Fuel type diesel -409. Okay? So I for natural gas -1063 and I for, oh god, I forgot it already, diesel -409, right? -1063 -409. Okay, so diesel. Okay, each one of these variables can be +1 or -1. Okay, so therefore it's +1 if the car is using natural gas, right? And -1 otherwise. Okay, otherwise. And diesel, same thing. +1 if diesel, and -1 if diesel, and -1 otherwise. Okay? So this way, essentially, the interpretation is a little bit different. Okay? from 0 and 1. If we're using +1 and -1, that number, which comes from the regression output, okay, indicates by how much that specific feature of the car is above or below the average price of the vehicle with all possibilities. Okay, so I'm going to explain a little more. If I take a car with a certain mileage, certain horsepower, certain age, etc., etc., okay? Let's say Toyota Corolla with 10,000 miles on it and, I don't know, 20 horsepower or whatever the number can be, okay? Some of these Corollas can be powered by gas, some can be powered by diesel, and some, who knows, can be powered by natural gas, okay? So if I average them out, all of these different fuel types, same type of cars, same mileage, same horsepower, but different fuel types that they're using, okay? Then I'm going to get an average price for that mileage, for that age, for that horsepower. Taking into consideration all different fuel types, okay? Now, if I take this average level and I want to see which type of the car is more expensive and less expensive, okay? Compared to the average level, the car with natural gas is going to be less expensive by $1,063 than the average, okay? A car with diesel fuel is going to be $409 less expensive than average. But then the question becomes, okay, what do we do with the cars which are gasoline, right? Well, for gasoline, so if it's +1, it's getting multiplied by this, right? So if the car is natural gas, then we have +1 over here, and multiplied by 1,063, it tells you that natural gas is lower than average, the price of the vehicle, lower than average by $1,063, right? If it's a diesel, then for natural gas we don't use anything, but for diesel we use +1, okay? So diesel basically says, well, that car is $409 less than the average price of the vehicle, with that mileage, that age, and that horsepower. What if the car is gasoline, right? So for the gas cars, or petrol, how they call it, right, in this file, we have to use ing, the first dummy variable, -1, and I diesel, -1 as well, okay, indicating that it's not a diesel, and it's not natural gas, it's something else, okay? So therefore, that is getting multiplied by -1, that is getting multiplied by -1, so they become plus, right? And I add them together, right? And what's my answer? My answer is something like 1,472 or something like that, right? And that's a plus sign because I used minus, and both of these slopes are minus, right? They're negative. Agree? Minus times minus, and then I add them together. That's what it's going to be. And if you go back to our output, where is our output? It's right here. That's actually, that's what it says, right? It says, based on the fuel type, if it's, that's part of my prediction equation, right? If the car is on the natural gas, it's minus 1,063. So whatever value you compute from age, horsepower, mileage, blah, 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 if it's natural gas, you have to subtract from that value $1,063, right? So natural gas cars, everything else being equal, are less expensive by $1,063 than on average, right, these vehicles, okay? Diesel cars are going to be $409 less expensive, right, than average. Gasoline cars, didn't we just compute that? We did, right? Minus 409, minus 103 with a plus sign gives you 1,472, right? And that's what the last one says. 1,472 with a plus sign, right? So gasoline cars are more expensive than average by 1,472, okay? So now we kind of included this variable. So if I ask you, for example, if I have two cars, same exact thing, right? Same age, same horsepower, same mileage, but one of them is gasoline, petrol car, right? And another is, for example, diesel. What kind of difference in terms of price can I expect from them? Can you infer that from this output? You can, right? Because if everything else is the same, right? Age, mileage, horsepower, all of them, right? Gasoline car is going to be 1,472 plus, right? More expensive than average, right? Diesel is going to be 409 minus. So the distance between them is going to be what? If you add these two numbers together, is going to be like $1,881, right? Correct? So here's how it looks, right? Let me add a visual representation. So this is the average level, right? The gasoline cars are right here. This is gas, right? Gas means plus 1,472, right? Compared to the average. Well, look at that. It's a different color all of a sudden. I don't know why. How it happened. Okay, so here is, oh God, it's a marker. Okay, here is my diesel, right? And diesel is 409 below the average, right? And so what's the distance between the gasoline and the diesel? Well, it's your 472 plus 409, right? That's all the difference. Agree? So same cars, but one of them is gas and another is diesel. The price differential between them is going to be these two numbers added together, right? And? 1881. And you agree? You look a little like confused.
No, I'm reading blue. You're good.
Oh, okay. Yeah, the blue sucks. I agree. I'm going to change that. Hold on. How do I change that? Yeah, that. So here we have 409, and here we have 1472. Okay, and therefore the total difference is going to be 81. Okay. Yep. Make sense? So that's how we include the non-continuous categorical variables into the multiple regression. Okay, it's a little awkward, but it can be done. All right, and a lot of regression equations actually they do require that. For example, what's the first rule of real estate? Do you know? Location, location, and location, right? So I can actually, that's one of the problems which is very legitimate in the area of real estate, right? Can I predict the price of the house based on the house characteristics, such as, what do you think is the most important, well, aside from location, numerical characteristic of the house that determines the price? Square footage, right? How large is the house? Is the amount of land important? It is, right? Is number of bedrooms important? It is. Number of bathrooms. And how many cars can fit in the garage? It can be 0, no cars, right, attached. Okay, but there are some other things, such as, for example, pool. Do they have pool or do they not have a pool? How do you insert that variable into the equation? That's how, right? You insert a dummy variable that says 0, 1. If the house has no pool, that's a 0. If the car has a pool, that's a 1. Okay? So, let's take a look at other two, right? So we kind of covered the fuel type, right? But we remember there are two more, right? One of them is color of the car. But on the color, we say it's either metallic color, cool looking kind of, silver-ish type of car, right? Or not metallic. Not metallic is like a bunch of other possibilities, right? What's the difference? Okay, so here, metallic, minus 29, and it's again same deal, right? Plus 1 or minus 1. So if the car has a metallic color, what impact does that have? Metallic 0. So it says this one goes with metallic 0. I'm guessing it's a non-metallic color, right? So if the car is non-metallic color, then its price is $29 less than average, right? But what if the car is metallic equal to 1? Then we have to use minus 1, right? Times that number, so it goes up by 29, right? So cars that are metallic type, they are $29 above the average. Everything else, all other cars, they are $29 below the average. So the price differential apparently between metallic and other colors seems to be twice as much, right? 29 times 2, so it's $58, right? So if the car has a metallic color, it seems that it will be $58 priced above other colors, right? And same thing happens with automatic, right? I'm guessing we have same encoding, right? Automatic 1 means car has an automatic transmission, right? 0 means it's a non-automatic manual transmission, right? So right there it says if the car is automatic, 0 means it's manual, right? Then I have to take 1 and multiply it by minus 119, right? So manual cars are priced $119 below the average, right? What happens if the car is automatic equals to 1? Then I have to multiply that by minus 1, because that model's automatic 0, right? And I'm talking about automatic 1. So you have to multiply it by minus 1. Therefore, minus 19, 119 becomes plus 119, right? So automatic cars are priced 119 above the average. So kind of, if you ask what's the difference in terms of the price between manual and automatic, well, let me take a picture of that, right? Here, right? So my variable is automatic, so that it becomes more clear, 0, right? And that comes with this with a slope minus 119, right? Automatic 0 means what? Manual, right? So this is manual car, manual, and it can be either plus 1 or minus 1. So if the car is manual, right, I multiply it by plus 1, and therefore it goes 119 below the average, right, because it's minus 119, okay? So this is where the manual cars are located, okay? But if the car is automatic, it becomes minus 1, right? So minus 1 times minus 119 gives me plus 119, and therefore plus 119, that is automatic car, right? So if you ask the question, how much is the difference between, how much value does the automatic transmission add or subtract whatever it is to the car, then here's the answer, right? All manual cars are priced 119 below the average, all automatic cars are priced 119 above the average. So the differential between them is what? 238, right? So same car, same age, same fuel type, same mileage, horsepower, same thing. But one is manual Corolla, another is automatic. Same exact thing, but automatic transmission. You can expect to pay $238 more for the automatic car than you are for the manual, right? Make sense? Okay, cool. Any questions, ladies and gentlemen? Because we're standing at a historical moment. This is the end of the simple linear or multiple linear regression for us. Any questions? Concerns, complaints, sarcastic comments? Okay. Well then, let's get started with a natural extension, okay? Natural extension of this topic, which is called logistic regression. Okay, so I'm going to start a new slide here, and I'm going to write it out. Quite honestly, I don't have slides prepared. They're kind of in progress. Okay, I'm going to post slides as we go, but I don't have slides prepared for this one. Logistics, not logistics, but logistic, not S. Regression. Okay? Now, logistic regression is a very popular and also very powerful tool, I got to tell you, okay? It's used a lot. Logistic regression does exactly the same thing as the classification tree. Remember, we studied classification trees about a month ago, right? And we used several examples in classification trees, right? We said, here's the Titanic example, right? Some people will survive, some people will drown, and that's our target, right? Being able to predict who will stay alive and who will drown based on gender, class that they travel, and what else? Like child versus adult, age, let's call it age, right? And then we looked at, I believe there was a problem, who will buy the lawnmower, right? People can either buy or not, and we looked at how big of the yard they have and how much income they have, right? Then we looked at bank, I believe, right? Loans from the bank. Who will default on the loan and who will not default on the loan. And we had a bunch of predictor variables, right? That's what we did in classification trees. Logistic regression does exactly the same thing. It's a classification model, okay? So therefore, when you're dealing with logistic regression, your target is categorical. Target is categorical variable. Categorical variable. So therefore, essentially, you're dealing with classification. Not prediction, such as regression analysis, that's prediction, right? If you know the mileage on the car and the horsepower, can you predict the price, right? If you know the square footage of the house and number of bedrooms, can you predict the price? If you know how much we charge for the product and how much we spend on advertising, can you predict the sales, right? If you know, for example, let's say, parks, right, such as bush gardens or water country, one of the biggest problems that they're dealing with every day is staffing in terms of who will come to work, right? Any of you worked in bush gardens or water country during the summer? I had a couple of students this summer. One worked in Busch Gardens, one in Water Country. And one of the biggest issues for them is predict sales, and sales are driven by attendance, right? They want to predict attendance of the park. Okay? And also they need to staff appropriately. So every day is kind of a guessing game for them, right? How many people will come to park? Therefore, how many people I need to come to work? So they have a regression model, okay? Predicting how many people, number of thousands of people who will attend the park today. It's based on a lot of things, like on yesterday's attendance. Can be based, what else do you think predicts how many people will attend? Weather, in terms of what? Weather is general statement.
Sunny, rainy.
Sunny versus rainy. That is what type of variable? Categorical or numerical? Sunny versus rainy. Categorical, right? And moreover, because weather is, how can you predict, right? I mean, you can look up the forecast, but can it be wrong?
Yeah.
Oh yeah, it can be wrong, right? So you use the forecast to insert your categorical variable, just like what we did right now, right? Is it manual or is it automatic? Is it going to be sunny or is it going to be rainy? Temperature, does that affect anything? Temperature? Probably does, right? Humidity, atmospheric pressure can affect things, right? Day of the week? Yeah, right? Most people come on the weekend, right? Holiday versus the regular day? Yeah. All of these things can be factored in, right? So that basically is an example of predictive model, right? We're predicting a numerical variable. Classification trees and logistic regression does things differently, right? We're not predicting a number, we're predicting a classification. Will that person stay in the university or will they drop out? Okay? Will that employee keep working for us or will they leave to a different job? Will that customer default on the loan or will they pay it back? One of the biggest, I probably told you that before, I don't remember, one of the, where the data analytics came from. It actually came from two industries, okay, originally. Banking was one of them, predicting, who will default on the loan and who will not default on the loan. Another factor pushing kind of industry behind data analytics was cell phone companies, telecommunications. Okay, how so, you can ask, right? Well, here is the story, ladies and gentlemen. Cell phone market in the United States reached the saturation, right? I have a cell phone. Can they sell me the second one? No, right? I don't need a second one. So when you have 300 million people, each with a cell phone, that's it. You're done growing, right? Can do nothing else. So from that standpoint, from the cell phone companies, how do they gain or lose business is by stealing or losing customers to the competitors, right? There are four big companies, right, that basically divide the market. What's that? T-Mobile, Verizon, AT&T, and there is another, Sprint, right? So essentially, all the game between these companies is, can I steal, my competitors' customers? That's it, right? And sometimes, you sign up a contract with them, they piss you off, right? Every once in a while. Like, they drop the calls, you call their customer support, they can't answer your questions, they have weird fees, right? So you basically say, okay, I'm going to be out of the contract in 3 months, and then I'm switching over to Verizon. I had it with them. So they build the models that will allow them to predict based on the usage, how much you use your service, right? Whether you go over the limit, whether you're using, your data plan extensively, how many support calls you placed, okay, when your calls are mostly in the evening, during the day. So all these things about you, right? How likely you are to switch to a competitor in the next when your contract expires. So they actually do run that kind of model. So the whole data analytics kind of came out of these two industries. Banking industry, giving customers loan and making sure they don't default, and the telecom industry, okay, making sure that customers are staying your customers. Okay, logistic regression. It's a little bit weird model. But let's actually start with, let's close out this file, okay? And let's go ahead and open up the file that we used long time ago. This one, right there, Universal Bank CT. Let's see if we can kind of get us started with logistic regression, okay? So in this file, there it is, okay? Personal loan. All right. No, it looks like actually, hold on, the value labels. Yeah, value labels, right there, okay? So, if you go and take a look at this, this is my target column, right? Personal loan. When you downloaded the file, you probably can see yes or no, right? Yeah. So go ahead and double click on that, all right? And it turns out that we have a value labels. I don't remember if we discussed, we probably discussed it at the beginning, right? Value labels. So in actuality, data type is numeric, and the actual data is 0 and 1. But we label them as yes, no, and that's what's showing up, right? So if I go ahead and unclick that one, use value labels, and then click OK, instead of yes, no, it will show 0, 1, right? Yeah, sure. So if you double click, so go into the column properties, right? Value labels. If I use value labels, it shows yes, no. But if I say don't use value labels, use the original data that was there, okay, unclick that, and it's 0, 1. And moreover, what I just did is I changed that from nominal, it was nominal, right? Right triangle. Because my target is 0, 1, it's a number, right? What the heck, it's a number. Right? So go ahead and change that to a continuous variable. So let me do this, ladies and gentlemen. If my target is a number, I just made it a number for crying out loud, right? And I have a bunch of predictors. Let me run. What's the most natural thing to do in this scenario? My target is a number. What kind of model, what kind of predicting model do I use? If my target variable is numeric, just like in predicting the car price or house price, I can use multiple regression, right? It can predict for me a number, 0 or 1. Okay, let's go ahead and do that. Let's fit the model. So what I'm about to do is actually a stupid thing, okay? Don't ever do it in real life, all right? So I'm using personal loan 0, 1, and I'm going to select everything else as model effect. So I'm going to click add, and then run the model. And software doesn't care really, right? Software will do exactly what you tell it to do, okay? You want a model? Here is the model for you, my friend, okay? It can be bad or good. R squared, probably not that good. Yeah, not good at all, okay? But here is the model. You asked for it, okay? All right, so can I remove the variables from the model? Because right now it seems a little excessive, okay? Let's say that I want to model my likelihood, like 0 or 1, based only on income. So if I select all the variables, holding down the control button, right? If I'm going to select all the variables except income, I'm going to leave income in. I'm going to assume that income is the only thing that's important, everything else is basically expendable, right? And I'm going to say remove. Bam. So that's the only thing that's out there. Here is my variable. Here's my model. Minus 0.14 plus 0.0032 times income, right? Well, let me write it down. Okay? So my model is loan default. That's my target, right? That's what I've selected as a target. Loan default, 1 over 0, is oh God, what was that? Minus 0.14 and 0.0032. So minus 0.14 plus 0.0032 times income. That's my model, right? Very simple model, okay? Slope is positive, right? Weirdly enough. That means that the more income a person generates, what happens to the loan default? Is it getting close to 0 or is it getting close to 1? If the slope is positive. To 1, right? The more income, the higher likelihood, the closer it is to being in default, right? That's a little counterintuitive, right? But I told you that what I did is a stupid thing. Here's why, ladies and gentlemen, okay? Really, my variable can be either 0 or 1, right? That's it. But if I plot it against income, okay, then slope is the intercept is negative, and the slope, positive slope, looks like that. And moreover, it goes into the negative area as well, right? Is that a good thing or is it a bad thing? Not a good thing, right? Because first of all, I understand these 2 points, right? Where I have either clear 0 or clear 1, right? What happens if I have things in between? Is it a 0 or is it a 1? Don't know, right? Even worse. What if my point is right here? What if my point is right here? Oh my God, right? So my equation, my linear equation, goes from minus infinity to plus infinity, right? And I only wanted this 0, 1 kind of thing, right? So linear regression is not a good thing to use when you're dealing with categorical variable, okay? But the method that we're about to start is called logistic regression. So see that keyword regression is in there. So it's actually a model that allows me to predict 0 or 1 outcome using a linear structure, like the regression that we just studied, okay? Now, how much time do we have left? Hold on. 3 minutes. Okay, let's get started, okay? Oh, kind of. I mean, we can still accomplish something in 3 minutes, right? Okay, the reason why it's called logistic regression is because it's using something called logistic function, okay? Logistic function. Oopsie. Function, okay? Here's the logistic function, ladies and gentlemen, okay? It's y equals 1 over 1 plus e to the power minus x, okay? Simple as that. Sometimes it's also called, well, let me first actually draw the kind of the graph of this function, okay? So what happens, so this is my x, okay? This is my x. What happens if my x is really, really small number? So therefore, let's call it minus infinity. Okay? Let's see. If x is equal to minus infinity, okay, I have 1 over 1 plus e to the power minus infinity, right? Therefore, it becomes e to the power plus infinity, right? Essentially. Agree? One of my professors used to say, yes, 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 agree, agree, agree. Drove me nuts, quite honestly. I'm like, oh, come on. Don't say that. Yes, 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 agree, agree. So, e to the power, how much is e to the power of plus infinity? Oh, come on. E to the power of plus infinity. Anybody? I'm feeling lonely here. It's Friday, plus we're out of time, right? Okay, let's do this. We're going to start slowly then, okay? Because I feel that I'm overstepping the mathematical boundaries here a little bit. Okay, so tell me, ladies and gentlemen, here, this is my x, and this is e to the power of x, okay? How much is e, by the way? E is the number, right? Anybody remembers at least three values in the number e? E is 2.72, something like that. Do you remember exponential functions from calculus? Math 135? No? It was a long time ago? It was a long time ago. Okay. All right. Well, here's my 0, right? 0. How much is e to the power of 0? Well, let me ask you differently. How much is any number to the power of 0? It's 1, right? It's 1. Okay. So therefore, 1 is where it goes through, okay? When x becomes positive and large, e grows like that. Very, very rapidly. More quicker than the linear function, okay? If x becomes negative, it approaches 0, like that. Okay, so this is e to the power of x. Okay? E to the power of x. Alright, I'm going to keep that intact until Monday, and we'll take it from here. So we're going to go back to our logistic function, and we're going to figure out how exactly the logistic function looks, okay? And why is it used, therefore, in order to model categorical response. 0, 1, yes, no, true, false, survive, die, male, female, default, non-default, that kind of situation, okay? So that's it for today, and I'll see you on Monday. And don't forget that there are projects assigned, right? And there is 1 week of time left. And most of you are procrastinating right now.